I welcome you all in sixth session of your Physics Paper 1 syllabus. In today's session, we are going to discuss the phase velocity and group velocity. So, let us consider there are few students who are just ready for running race. So, after some time when race gets started, different students will achieve different position. Why they haven't achieved the same position like in a queue? Because all students are having their own speed. So depending on their speed, few students are leading whereas few students are lagging behind. Same is the case for waves. Suppose few waves have been started at certain time, say at initial time t equals to 0. When all these waves start propagating in forward direction towards the target, depending on the speed of each wave, few of them will go forward and few of them just remain in backward position. Now, the velocity of this individual wave, velocity of wave A or velocity of wave B, wave C, wave D, wave E, this individual velocity, we refer it as the phase velocity. Whereas when these waves get traveled all together, the combined velocity of this assembly, the whole assembly, we call it as the group velocity. Thus, all these individual waves travel with so-called phase velocity, denoted by Vp, whereas the assembly of all these waves, which form a group, this group altogether moves with a velocity known as the group velocity, denoted by Vg. So this is the physical meaning of phase velocity and group velocity. Now, as we have seen earlier, when we combine two waves with different frequencies, omega 1 and omega 2, we will get certain beat pattern. So in this beat pattern also, the movement of individual wave, denoted in red color, is different, whereas the propagation of the resultant wave, denoted by this blue envelope, is different. So this wave is propagating with so-called phase velocity, whereas the combined envelope of these two waves is propagating with a velocity well known as the group velocity. Now let us see what is the mathematical expression for phase velocity. There are two ways by which we can obtain the expression for phase velocity. The first way is very simple one. Let us consider a wave propagating in forward direction. Now we know speed is nothing but distance divided by time. If we consider one oscillation of a wave, for one oscillation the distance travelled is equals to wavelength lambda, which is equals to 2 pi by k, where k is the propagation constant. Whereas for one oscillation, the time taken by the wave to complete one oscillation is the time period capital T, which is equals to 1 by nu, is again equals to 2 pi by omega, that is the angular frequency. So taking into account these things, for one oscillation, we can write down the expression for speed equals to lambda by t, which is equals to omega by k. This ratio omega by k we call it as the phase velocity Vp. Thus, if we know the expression of a wave, then we can obtain the phase velocity just by substituting the value of angular frequency divided by propagation constant. So this is one way by which we can obtain the mathematical expression of phase velocity. There is another way, little complicated one. Let us consider a wave moving in positive x direction. A wave moving in positive x direction is represented as y equals to a sine omega t minus kx. Now, this is, say, the wave at t equals to 0. The same wave after some time interval delta t will be like this. Now, here in time interval delta t, the wave will cover the distance delta x. So the speed is nothing but delta x by delta t. Now, if I focus on each and every point of this wave, say, for example, we consider this point A. The point A is found to retain its original displacement, y displacement, after some time. So, not only A, but each and every point of this wave is trying to retain its original y displacement. So, which is the factor which is actually giving rise to y? Here, this factor omega t minus kx, this bracketed term, is actually giving rise to variation in y. So, if we say a particle or a point on a wave is trying to retain its original y displacement, that is, it is trying to keep y constant, then we can say this bracketed term is equals to constant. So, omega t minus kx equals to constant. Taking the derivative of this equation, we will get omega minus kx dx by dt equals to 0. So, the expression for dx by dt, what we call it as the phase velocity, is found to be equals to omega by k. Thus, again we have obtained the expression for phase velocity to be equals to omega by k. Now, let us consider the mathematical expression for group velocity. Let us see how we can obtain the group velocity of waves that get combined to form a resultant wave. Let us consider two waves that are traveling in positive x direction, y1 and y2, with their angular frequencies omega 1 and omega 2 and propagation constants k1 and k2 respectively. Before applying the superposition principle, let us consider few things. Let omega is the average frequency, k is the average propagation constant of these two waves. Let delta omega is equals to omega 1 minus omega 2 divided by 2 and delta k equals to k1 minus k2 divided by 2. Now, the resultant wave y is given by y equals to y1 plus y2. Substituting the values of y1 and y2, we will get y to be equals to a sine omega 1t minus k1x plus a sine omega 2t minus k2x. Now, here we are going to use sine plus sine formula. Substituting that formula and keeping in mind these arrangements, we will get the expression for resultant wave y to be equals to 2a cos delta omega t minus delta kx into sine omega t minus kx. Now, in this expression, the sign omega t minus kx is the usual part of a propagating wave. So, whatever is there in association with this factor represent the amplitude of wave. In our case, this represents the resultant envelope of two waves y1 and y2. So, in order to obtain the group velocity, we have to obtain the expression for velocity for this particular component. Now, as we have obtained previously in phase velocity, the group velocity could be written as coefficient of t divided by coefficient of x. Coefficient of t divided by coefficient of x. So, it is nothing but delta omega by delta k, which we can write down it as d omega by dt. This is the expression for group velocity Vg. Now, once we know the mathematical expression for phase velocity, mathematical expression for group velocity, let us see what is the relationship between these two velocities. We know the phase velocity is equals to omega by k, so that omega is equals to phase velocity into k. But the group velocity is derivative of omega with respect to k. Substituting the value of omega, we will get Vg, that is group velocity, to be equals to phase velocity Vt plus k into derivative of phase velocity with respect to k. This is the expression in terms of propagation constant k. We can even rearrange this equation so as to get the relationship in terms of wavelength. We know the relation k equals to 2 pi by lambda. So, this derivative equals to minus 2 pi by lambda square into d lambda. Substituting this value of dk as it represents the total derivative, substituting this value of dk in this expression, we will get group velocity equals to phase velocity minus lambda derivative of phase velocity with respect to wavelength. This is the relationship between phase velocity and group velocity. Group velocity is found to be equals to phase velocity minus a term. What this particular term indicates? It indicates the variation in phase velocity with respect to wavelength or with respect to frequency. So, this term indicates the variation in velocity, phase velocity with respect to wavelength. What if there is no any variation of phase velocity with respect to wavelength? If there is no any variation of Vp with respect to lambda, then this term will become 0, and what we will get? We will get group velocity equals to phase velocity. Such a medium for which we are getting group velocity equals to phase velocity, we call this medium as non-dispersive medium. Non-dispersive medium, a medium in which the speed of wave is independent of its wavelength. As wavelength changes, what we expect is speed should be changed, but in case of non-dispersive medium, the speed remains independent of wavelength. Such medium we called it as the non-dispersive medium. For example, for sound waves, the air is acting as a non-dispersive medium. We can hear sound as it is, which propagates through the air. So, air will act as a non-dispersive medium for sound waves. Likewise, we collect the information of far apart astronomical bodies by collecting the light from them. So this light travels through space. The space is again acting as a non-dispersive medium for light coming from the astronomical bodies. So, for non-dispersive medium, group velocity is found to be equals to phase velocity. Now, what if this particular term is not equals to 0? If this term is not equals to 0, that is, speed of a wave is not independent of wavelength, rather it depends on the wavelength, then such medium we called it as the dispersive medium. The medium for which the speed depends on wavelength of the wave. We called it as the dispersive medium. What is dispersion? The phenomena of dispersion is not new to you. You have seen rainbow for many times. You have seen the splitting of white light when it passed through prism. This is an example of dispersion of any wave. So, in case of dispersive media, the phase velocity is not independent of wavelength, so that this factor doesn't become zero. As a result, we say in dispersive medium we will not get group velocity to be equals to phase velocity. Rather, if this particular factor is positive, that means speed is increasing as wavelength is increasing. So if this particular factor is positive, then group velocity is found to be smaller than the phase velocity. Group velocity is found to be smaller than the phase velocity. Such a medium for which group velocity is found to be smaller than the phase velocity, we call this medium as the general dispersion medium. General dispersion medium. Whereas in case where this particular term is negative, that means speed increasing when wavelength decreasing. So if this term becomes negative, then in that case group velocity becomes greater than the phase velocity, because that negative becomes positive, so group velocity becomes greater than the phase velocity. And such a medium for which group velocity is greater than the phase velocity, this medium is known as the anomalous dispersion medium. Anomalous dispersion medium. So, whenever we consider this relationship between phase velocity and group velocity, we have to consider three cases. First one of non-dispersive media, where this term is 0, so that Vg equals to Vp. Next, we have to consider dispersive medium with general dispersion. General dispersion, for which this term is positive or group velocity is smaller than phase velocity. We call it as the general dispersion media. In next case, when this term is negative, then in that case, Vg, group velocity Vg, is greater than Vp. We call such medium as anomalous dispersion medium. So, these things have just been structured here. In case of dispersive medium, this factor is 0. While passing through the dispersive medium, the wave don't change its shape, but while passing through dispersive medium, wave changes its shape. For non-dispersive media, phase velocity equals to group velocity, while for dispersive media, phase velocity could either be greater than group velocity or phase velocity could be smaller than the group velocity. So, this is all about the relationship between phase velocity